Application of the first law to motivate the use of property called as enthalpy. Let's imagine an adiabatic process, an adiabatic steady throttling of a gas which is passing through a valve or any other restriction. So let's imagine like we have got a wall somewhere here, and a gas is passing from the upstream, which actually is at state 1, to the downstream, which is actually at state 2 somewhere. Let's imagine like the pressure at the upstream is V1, volume V1, and internal energy U1. And let's say the pressure at the downstream is equal to P2, volume V2, and internal U2. Let the process be adiabatic process. That means like there should be no heat flowing into and out of the system. So there is actually a restriction that there is no energy, and heat energy is getting into the system, and then there is no heat energy which is leaving out of the system. So there is the process is adiabatic process, and the process is also the steady flow. Steady flow, like there is no actually change in the kinetic energy, there's no change in the mass, and there is no change in the velocity, like this. So let's say first thing first, we would define what actually we mean by the upstream and what do we mean by the downstream process, and what, or in other word, what is actually state 1 and what is actually state 2. Let's imagine like the above, in a above pipe. Let's imagine like we have got a volume, sorry, a valve, at state 1. What would happen that there is a volume of a gas, and that volume of a gas is somewhere, we would say like we have got imaginary piston, let's say, and we have got a volume of a gas which is somewhere at state 1 over here, and that means like we would be having a pressure P1, volume which is actually over here V1, and internal energy U1 over here. So this is actually our state 1. Please make sure like the valve is including in the system. I would explain it a little bit later as well. Then I'm going to the downstream. That means like I am actually moving this volume over here to volume somewhere over on this side, which is actually at state 2. So what is actually state 2 now? State 2 would be somewhere, let's say again, imaginary piston and cylinder, sorry, piston. So that means like I'm moving from that state which was actually up here as well. I'm moving this volume to state 2, which is somewhere here. Make sure if you can, and that's what actually it would look like. Initial state, that would be state 1. So we have got a volume pressure P1 here, volume V1 here, and internal energy U1 here. And we are moving this whole thing from this side of the wall to another side of the wall, which is actually at the final state. Can you just imagine like the valve itself is including in both of the system or both of the state? This is just a very quick imagination. Like if I'm talking about, let's say, I'm inside this in the class, and I'm actually going outside the class. So that means like the door itself is common between inside and outside. So if I'm inside the door, that means like I'm inside the class, and if I'm outside the door, that means like I'm outside the class. So in other word, if I'm saying like if I'm on this side of the wall, then I'm on a state 1, and if I'm on this side of the wall, I'm on a state 2 actually. So we define this system in a very simple manner. Like we have got a pressure P1, volume V1, and internal energy U1, going from state 1 to a pressure P2, volume V2, and internal energy U2 actually. Going to the first law of thermodynamics, and that's a what kind of a work it is actually. If I'm saying like I'm moving from state 1 to state 2, so let's say if I would say like change in internal energy would be equal to heat supplied minus work done. So that is my first law of thermodynamics. So as the process is adiabatic, so that would be somewhere here. So change in internal energy would be equal to minus W. Now let's say what kind of a work it would be. That would be equal to the flow work. What is actually a flow work? The flow work is actually the pressure P1 which would be pushing the volume V1 from the wall to a pressure P2 and the volume V2. That means like the pressure P1 is responsible to push the volume V1 from the wall from the upstream to the downstream. So in other words, what would be the work done itself? The work done would be equal to W would be equal to P2 V2 minus P1 V1. That means like the pressure at the final multiplied by the volume at the final minus pressure in initial and volume at the initial. So that would be actually equal to this. So that means like this is what we call it or what we would define as the flow work. Now moving up there back to the equation which is somewhere here or just over here. So the change in internal energy would be equal to, or in other words, change in internal energy is equal to minus W. In other words, U2 minus U1 would be equal to P1 V1 minus E2 E2. Make sure I've changed the sign, and P1 V1 minus P2 V2 would be there. Just moving or rearranging this one, that would be equal to U1 plus P1 V1 would be equal to U2 plus P2 V2. That means that the sum of internal energy and the flow energy initially is equal to the sum of internal energy and flow energy finally. Or in other words, the total energy which was present in the system at the upstream would be equal to total energy at the downstream in a throttling process, in a process in which actually the volume move from state 1 to state 2. Now this property which is actually U plus PV, this property or this quantity is defined as the enthalpy. What is actually enthalpy itself? Enthalpy itself is sum of internal energy and the flow energy. In other words, what I'm saying, like if you have got the internal energy in a system and if you have got the flow energy in a system, the sum of them two energy would be equal to enthalpy. Now make sure over here, if internal energy is missing in a system, so you cannot call enthalpy as flow energy, because flow energy itself is an energy itself. If the flow energy is missing in a system, you cannot call internal energy in a as a enthalpy. So enthalpy would be only and only defined when both of the energy, which is actually internal energy, and the flow energy, they are present inside the system. So enthalpy is a property which is actually defined as a sum of internal energy and flow energy. Now again, moving back to the what actually we have said, like what is actually enthalpy or what is actually enthalpy energy. It was the energy which was responsible from moving the volume V1 from upstream or from state 1 to volume V2 which was actually at state 2 now. So that means like when we are talking about the enthalpy mean like there is actually a flow energy in a system, there is actually internal energy in a system, and when this flow energy and internal energy move from one state to another state, then that mean like we are moving from one enthalpy state to another enthalpy state. Enthalpy again would be defined at the term of um, microscopic level, and enthalpy again is defined as the state function. So we have defined different state function right now. We have defined pressure as a state function, temperature as a state function, volume as a state function, internal energy as a state function, and now we have defined enthalpy as a state function too. We are left with one more property which will be defined in a second law of thermodynamics, and that was what actually we call it as the entropy. So we have defined many state function in what we will be using in a thermodynamics. Yes, you can read it out, and if you have got any question, you can raise it into your classroom. Now, in your previous knowledge, you might have defined enthalpy as the total energy. So that means like enthalpy is a total energy. That is correct when we can say like the process was adiabatic, when there was no other work done in it. So the only and only energy we were having was the internal energy and the flow energy. So that's why it was called as the total energy. Enthalpy is also sometimes called as the heat content of the system. So it is only and only called as heat content of the system when we are talking about the isobaric process. When the heat is supplied in an isobaric process, we will be actually just deriving this equation right now. So let's say quasi expansion or quasi static expansion of the gases, and that is actually at a constant pressure process or isobaric process. So let's say having first law of thermodynamics, first law of thermodynamics is equal to change in internal energy plus work done. So heat supply is equal to change in internal energy plus work done. So if it is a constant pressure process, so constant pressure process P V2 minus V1 is equal to work done, if you can imagine, and change in internal energy is equal to U2 minus U1. Just open it up, and that would be U2 plus PV2 and U1 plus P V1. So you can imagine you have got the internal energy, you have got the flow energy. You have got the internal energy, you can have got the flow energy. So whenever you have got these two energies, just bracket them and call it as the enthalpy. So Q would be equal to H2 minus H1. So I'm just writing in a total terms. So H2 minus H1, and that means like the heat supplied in a constant pressure process is equal to change in the enthalpy. So that's what we call it as the total heat content of the system. But that is what actually we call it as the heat supply in a constant pressure is equal to when we are talking about the change in enthalpy only. The first law in terms of enthalpy, let's say in our last few pages we did say like the internal energy would be equal to heat transfer minus work done. Now this work done for a quasi equilibrium process was equal to P dV. You can imagine like you have done a lot of time that's thing. So that means like change in internal energy would be equal to P dV. So PDV is equal to work done only and only in a quasi static process. While you can imagine like work done can be any kind of a work done. So the above equation, which is equal to change in internal energy is equal to Q minus W, it is true for any process, whether it is a quasi equilibrium process, whether it's any other kind of a process, non-quasi equilibrium process, irreversible process, reversible process. So this equation is true. But this equation, which is actually change in internal energy is equal to Q minus PDV, that's the only and only valid when the process is at the quasi-static process. Um, H is equal to U plus PV is there. So can you just put them? So H is equal to U plus P, just differentiate using a chain rule. or you just call it, I would say, like whether it's a chain rule or product rule, can you just change it accordingly if you think like it's not a chain rule or product. So just differentiate using the product rule. So dH would be equal to du plus edv plus vdp. Now u plus pdv is equal to heat supply, if I would say like, and VDP is there. Just say like this is actually the first law of thermodynamics in terms of enthalpy, and that is valid for the any process. Just moving them to equation over here. So this equation is valid for any process, and this equation is valid for the only and only for the equilibrium process. Thank you very much. I hope you would understand all of these concepts. If you have got any questions, please raise your in our classroom and I would be able to answer them.